Hey everybody, welcome to another interesting session in the math class. Today we are going to study the process of computing the inverse of a matrix using Gauss Jordan elimination. For those of you who do not know what is Gauss Jordan elimination, this is nothing else but the elementary row transformations that we make on a matrix, right? If you do not know about the elementary row transformations on a matrix, please refer to my previous video which talks about the elementary row transformations. The title of the video is What are elementary transformations in a matrix, right? You can just search like that in the math trail and you get the video, right? So once you've understood that, let's go to the whiteboard to understand the process of finding the inverse of a matrix using Gauss Jordan elimination. So here we go. So the core idea behind this is that let's say you have a matrix A, right? And then let's say you have a sequence of matrices, elementary matrices, which are like ek minus 1, ek minus 2, dot, 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 e1, such that ek into ek minus 1 into ek minus 2 all the way until e1 multiplied by a equals I. So suppose there's a matrix A, and then if you perform all these matrix transformations one after the other on matrix A, and that gives you the identity matrix I. If this is a situation, right? Then what you would do is just multiply both the sides by A inverse. So ek into ek minus 1 into ek minus 2 dot 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 into e1 and then dot A inverse equals I A inverse, right? So if you just look at this A inverse, right? This is basically happens to be I, right? Because A multiplied by its inverse should give you I. So ek into ek minus 1 into ek minus 2 dot 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 e1 into I equals, and this I into A inverse is nothing else but A inverse, right? So this equals A inverse. So now you see, if you look at this condition, right, this situation here, you find out that a sequence of matrices from ek to ek minus 1, if they can transform the matrix A to the matrix I, then the same set of matrices can transform the matrix I to A inverse, right? That's what it infers. So if you have a matrix A at the left-hand side and a matrix I over here, right? Then somehow if you can transform this matrix to I, then that means this side will be transformed to A inverse. That's what follows here, right? Because you have the same transformations here. If they are applied on A, then that gives you I. Then if they're applied on I, then that gives you A inverse. So somehow it follows that if you can transform this matrix to an identity matrix, then automatically this side gets transformed to A inverse. Okay, that's a method of finding A inverse. So suppose we have a matrix A. Let's say it's a 2 by 2 matrix and it's A, B, C, D, right? Then what you have to do is write it in this form. A, B, C, D, right? It's called as augmented form. And on the other side, you have to just write 1, 0, 0, 1. All right. So somehow if you can transform this to 1, 0, 0, 1, then this side will get transformed to something called as DEFG. And this DEFG is going to be the inverse of the matrix. Clear? So based on this idea, let's try to find out the inverse of a sample matrix. Okay, clear? right? So let's say we have a matrix A equals 4, 7, 1, 2. Okay. You have to find out A inverse. So the first step is write it in the augmented form. It's going to be like this: 4, 7, 1, 2 slash 1, 0, 0, 1. Okay. So somehow you have to now transform this to 1, 0, 0, 1. So this side will become A inverse. Clear? So let's do that using the elementary row and column transformation, which we have learned in the previous video. Okay. So what's the first step here? So somehow to convert this to a 1, what you can do is R1 is transformed to R1 minus 3 into R2. Okay, you have to do this on both the sides. So what do we get thereafter? So 4 becomes 4 minus 3 into 1, right? 4 minus 3 into 1. So which makes it 1, right? And 7 becomes 7 minus 3 into 2, right? Which makes it 7 minus 6. That is also equal to 1. And this remains 1, 2. So you have to do this on this side as well, right? So this 1 becomes 1 minus 3 into 0, which is 1. And 0 becomes 0 minus 3 into 1, which is minus 3. And then the bottom side remains the same. Okay. So now next step, we have to get a 0 in this place, right? So let's do R2 equals R2 minus R1. Okay. Let's do that over here. So what do we get? This 1, 1 at the top remains the same, and then row 2 becomes, this becomes 1 minus 1, which is 0. This becomes 2 minus 1, which is 1. Okay. And then the same thing on this side as well. This 1 minus 3 remains the same, and then 1 minus 0 minus 1 becomes minus 1, and 1 minus minus 3 becomes 4, right? Okay. So now the only thing that remains is you have to get a 0 at this point, which can be obtained by doing 1 minus 1. Okay, so you can do R1 equals R1 minus R2. So let's do that. R1 becomes R1 minus R2. So what do we get? So this 1 minus 0 remains 1, 1 minus 1 becomes 0, and then 0, 1. Similarly, you have to do the same thing at this side as well. 1 minus minus 1 becomes 1 plus 1, that is 2. Minus 3 minus 4 becomes minus 7. And then this remains minus 1 and 4. So we conclude that this is the inverse of the matrix because this has now become the identity matrix, right? 1, 0, 0, 1. So this is the inverse of a matrix. Let's verify this by multiplying this by the original matrix. So if this is the inverse of a matrix, then A inverse has to be I, right? So let's try that. So what is the original matrix? It's 4, 7, 1, 2 multiplied by the inverse 2 minus 7 minus 1, 4. 2 minus 7 minus 1, 4. So what do you multiply? 2 into 4 minus 1 into 7. So which makes it 8 minus 7, which is 1. Next step is minus 7 into 4 plus 4 into 7, which is minus 28 plus 28, which is 0. Then 2 into 1 minus 1 into 2, which is 2 minus 2, that is 0. And then minus 7 into 1, which is minus 7, plus 2 into 4, which is 8. So minus 7 plus 8, which is 1. So you successfully get I, which means that this is the inverse of a matrix. 2 minus 7 minus 1, 4. This is the inverse of this matrix, right? So in this way, using Gauss Jordan elimination method, by which is nothing else but elementary row transformations, we have achieved the inverse of a matrix. All right. So in the next videos, we'll see how do you find the inverse of a matrix using the adjoint and the determinant. So before that, we'll have to study many more concepts as well of determinants and the adjoint. So hold on to that. And I know excitement is due to follow. So I hope you like this session, right? If you want any more such videos, you want me to make them on particular topic, just comment on the bottom of the video, right? Until then, I wish you happy studying. And until then, take care, bye-bye, and see you in another episode. Thank you. If you like this video, please press the like button. For more such videos, subscribe to the channel. If you have suggestions for a new topic and would want to see a video made on that topic, please feel free to comment in the comment section below. Thanks for watching the video and see you in another video. Bye bye.